Hello everyone and welcome to yet another recreational programming session. How about that? So here we have a music visualizer that I started to work on some time ago, right? So it's pretty straightforward. You just drag and drop some music in here and it starts playing the music and visualizing it in a classical sort of FFT fashion, right? So fast Fourier transform. It's pretty cool, I think, but except it is not. In fact, it sucks. It actually sucks. Right, so if we take a look at the visualization of the similar style for the same song, one of such visualizations are available on the website that is called Bottle of Beats. It's a pretty interesting website, by the way. So people organize different competitions for the chiptune artists in there, right? So, and that song was actually submitted there by the author, right? So here is the entry. So I'm gonna keep the link to that entry in the description for anyone who's interested and stuff like that, right? And you can listen to the submission in here, and if you click listen, so it starts playing, and here is their FFT visualization. Look how cool it is, like, wow. It's just like, it makes so much sense. You can actually see the, like how the music plays and stuff like that. Ignore this line, because this line represents basically the samples, but the grayish part in here, and especially this part. Like, you can clearly see the notes that are currently playing right now. Like, why our visualization doesn't work the same? Like, why our visualization sucks so much compared to that? Right, so if we just like, try to do that again, like, what the hell is that? It kind of responds to the sound of the song, but it's just so janky, and there's these flickering frequencies, like a freaking high frequency. What the hell is going on, actually? And this is what I want you to do on today's session, right? I want you to investigate what the hell is going on and why does it suck so much. Well, you can also see the notes in here, but they're not as epic as on that website. No? Right. So anyway, to sort of understand, to investigate why it acts like that, we need to recap how does it even work? How does it even work? So essentially we have a buffer that holds the samples of the sound. Right, and essentially, what we do, we receive the samples of the sound in a callback periodically that is called from the sound thread. So sound thread periodically just grabs a chunk of the sound, like samples, and calls our callback with that chunk. Right, so here is the pointer to the beginning of the data, and this is how many frames this data contains. Frame is a pair of samples for left and right channel, for left and right ear. Right, and what we're doing here, we basically push that samples to the input buffer, to the global input buffer, from right to left, sort of like in a ring buffer fashion. And essentially that input buffer becomes like a rolling window over the playing song. Right, so it's basically smoothly rolling over the song. So, and then on each frame in a plug update somewhere here, what do we do with that window? Yeah, in here, if the music is playing, we're doing FFT on that input into the output. So essentially, we are transforming the time domain of that signal into the frequency domain. So out is the array of the same size, right? So if we take a look at the definition of this entire thing, it is an array of the same size n, right? But now it contains not the samples over time, but actually frequencies, right? So ith element of out is ith frequency. And it is complex, right? It is complex because the frequency can be actually offset, right? So because of that, we have to sort of keep track of sine and cosine of the frequency simultaneously. And the easiest way to do that is to actually use complex numbers, because you can do that through the Euler's formula, right? The Euler formula actually allows you to essentially keep track of sines and cosines simultaneously, right? If you're interested about the details, I recommend you to watch the first episode of this series. The link to the playlist of the series is going to be in the description as usual, and stuff like that. And then we are displaying those frequencies, right? But because the human ear doesn't really perceive the frequencies linearly, we are displaying them sort of exponentially. So specifically, we start with the frequency 20, right, for some reason. And then to get the next frequency, we're not adding some sort of like a step. We don't add 1. We multiply by the step. Specifically, I chose 1.06 because it's kind of like similar to how the frequency of the next note is calculated on a piano, right? So it's usually like the value that is roughly this. So you can actually pick any value, right? But it then grows sort of exponentially, and this is roughly how the human ear perceives the sound. And this is one of the reasons why on this website, by the way, the frequencies are displayed like this. You can see that the lower frequencies are actually sort of wider, and the high frequency becomes narrower and narrower and narrower, right? So it tries to sort of also, you know, replicate that sort of like an exponential logarithmic scale of the human ear, sort of, if that makes any sense. I'm not sure if it does, right? But yeah. So we're just basically skipping all of those things. And essentially that creates actually chunks of frequencies of increasing size, right? And we have to display a single bar for a chunk for the range of the frequencies. So as of right now, what I'm doing is just like I'm taking the average of them, which is probably not a particularly great idea. One of the things that I heard people suggested is to use maximum, right? So you have like a range of frequencies, and it makes sense to just like for that range, take the maximum, and that's going to be the good representation of what you have for that specific range. Maybe this is something that we can try to do actually. Right, so let's actually try to run the song. Let's try to run the song and see how we can modify it, because we have a hot reloading, so that means we can you know, explore and modify the code in real time, right, and see the effects in real time, so which is actually kind of good. Right, so let me see. So here we are basically iterating everything, right? Iterating the frequency for a specific chunk, right? For a specific chunk. And here I'm accumulating the frequencies, and then I divide by the size of the range, right? So if I want to do a maximum, right? So A is already 0, right? It holds the value of that is going to be used as the height of the bar. So it's already 0, so it's already minimum, which is all right. So let's actually assign the current amplitude to sort of like B. And if we found a B that is greater than A, this is the new value, this is the new representation, and we don't really have to divide by anything. Right, so we don't have to take an average or anything like that. All right, so that's really interesting. So it became jankier, and yeah. It's kind of interesting, right? And there's this frequency which is very high, and the reason why it is so high, because the frequencies are mirrored somewhere in the center. So since we're displaying everything logarithmically, the center is actually shifted somewhere here. So if we didn't display things logarithmically, right? If we display things linearly, it's going to be kind of different. It's going to be literally mirrored from left to right. So let's actually try to reduce the amount of samples, right? So because with a huge amount of samples, I don't think it's visible particularly that well. Right, and then let's try to do the linear representation of this entire thing. I wonder if we can easily do that. That's actually a very interesting question. What if I just do +1, right? So this is going to be +1. So we're not multiplying by step anymore. And this one is going to be temporarily f+1. That's a very interesting way of doing that, but yeah. So let me see. So do we use the step? Okay, so we don't really use the step anywhere anymore, so I can basically refresh. So I forgot the semicolon. Imagine asking for semicolon in 2023. Right, so we can kind of see that. It's still not mirrored because we're starting to display the frequencies not from the beginning, but from the 20. And the reason why we started to do that from 20 is because I thought that maybe they represent the actual hertz, and the lowest frequency that the human can hear is 20 hertz. But in reality, 20th frequency is not necessarily 20 hertz. It actually depends on the size of the window and the sample rate of the sound. So it's kind of like it was a little bit far-fetched. So I don't think like using 20 as like a low bar for frequency displaying is actually a good idea. So you know what? I think I'm gonna extract this 20 to a separate variable. I think I only use it twice and call it low f, right? And here is going to be a separate parameter that I can control now. Right, so let me refresh everything. Right, and let's actually say that the low frequency is going to be 1, right? So we're displaying everything starting from 1. And as you can see, they're mirrored. They're straight up mirrored, and this is because how FFT on the real signal works. I googled up like the reason why it is mirrored, and essentially it all boils down to the fact that the input is actually real and not complex. And when the input is real, the FFT just like mirrors everything, and the second half of the frequencies actually is not really useful for you. So you can basically ignore it. I do not fully understand the reasoning why you can ignore it, but like you can basically ignore it. You can literally see it, right? You can effectively see it. And this is something that we probably can do, right? So essentially, instead of iterating up until n, we can iterate up until n and half, right? So n and half. And let me actually refresh this entire thing. And as you can see, so now it's n. So let's actually add a little bit more samples, right? So yeah, that's a lot of samples. So can we do something like 3? Right, so yeah, so the more samples we have in here, the less we can see them, because at some point the width of the bar becomes less than 1 pixel, so we can't see anything at all. Right, and we're still displaying everything linearly, so let's actually switch to logarithmic scale, right? So let's actually bring back this step, right? So because it's going to be very much useful. So we're multiplying by the step, right? So this is multiplication by the step, now multiplication by the step. And the next thing here is computed by multiplication by the step. And I think this one is not particularly useful anymore, right? Because we're not computing the average. And it looks a little bit weird, doesn't it? Right, so let's increase the amount of samples. So we're starting to have these kind of weird gaps. And they're not going anywhere, by the way. We can keep increasing the amount of stuff. The gaps are not going anywhere. So we couldn't see them, by the way, before, because we had a low frequency equal to 20, right? So the low frequency of 20 kind of hides the fact that somewhere at the low frequencies we have these huge gaps. But as soon as you start trying to display like all of the low frequencies, it just like looks kind of weird. And the reason is how we calculate the next frequency to display. So imagine, like, we multiply by the step, and step is 1.06, right? So essentially, if your frequency is 1, and you're trying to compute the next frequency f1, and you multiply it by the step, what you're effectively doing, you're multiplying by 106, right? And then you need to use that value, which is effectively 106, as an index in an array. And since we're not doing any sort of floor or seal, it basically gets truncated, right? So essentially it gets truncated into 1. So effectively f and f1 are the same frequency, so effectively they're going to be displayed in the same place. And it will get like a lot of time until it gets to at least 2. So one way we can remedy that is essentially, instead of truncating it, actually always take a seal. So when we compute the next frequency, we multiply by the step, and we instantly seal it. So if it's going to be 1.06, it's going to become 2. And then it's going to become 3. And so on and so forth. So we basically do a seal. I'm not sure how correct that is, but our goal is to not have a correct frequency, right? Our goal is to have something cool looking, right? So I think in that case, it's totally fine to do this kind of thing, even though if it is not particularly correct. So, and every time we compute the next frequency, we have to do that seal, right? So f multiplied by step, and we have to do the seal. And in here, we also have to do the seal, right? So I think that's a good... All right, so that seems to be working. That seems to be working. So there is a kind of a weird flickering in here, right? There is kind of a flickering in here of some high frequencies, and I do not particularly understand where it is coming from. Right, so, but maybe it is coming from the fact how we compute the amplitude, right? So let's take a look. Yeah, so essentially the way we compute the amplitude is we take the real and imaginary part of the frequency and we take a maximum out of their absolute values, which is not particularly great way to do that. Right, so the actual amplitude, so we can think about the real number as actually a vector on imaginary plane. Right. So let me actually see. So yeah, so here is the real numbers and here is imaginary. So and we have a frequency and it's sort of some sort of a vector in here. And essentially what we're doing right now, we're taking this value and we're taking a maximum between them. And we're using that as an amplitude. So a more correct thing would be, and this is something that I actually heard in the comments on the previous videos, so thank you commenters who said that, you have to use this sort of magnitude of this vector, right? So, and it makes more sense, and it actually represents the amplitude of that specific frequency. So the direction kind of represents the phase of the sort of like a sinusoid, right, of sinusoidal signal, and the length represent like how like intense it is, its sort of magnitude, right, and that's the value we're sort of interested in. So we can give it a try. As far as I know, the standard C library has a function that lets you compute that magnitude. Right, so I think it's called CIBABSF, if I'm not mistaken. I think that's what it's called. Yeah. And essentially it will just compute the length of that vector. So it will take real part, imaginary part, square them, add them together, and take a square root out of them. So because that's how we compute the length of the vector. Right, so do they even say that anywhere here? So maybe they do. Yeah, there we go. Here it is. Hypot. What is hypot? Is that like a... Ooh, it's a function that computes the square root of the sum of the squares. I didn't know C had a function for that. That's kind of interesting. Did you guys know? What the fuck? Alright, so... okay, anyway. So essentially what we probably want to do, right, we want to replace this entire thing with just like return CABSF on the Z, right, so on the complex number, and let's see how it's gonna go. It didn't really help that much, right, so maybe that was not the problem with the flickering frequency. Maybe that was not the problem. So I think that might be something else. Right. I was trying to Google around how people use FFT for like music visualization and stuff like that, and I found a very interesting paper. Right, I found a very interesting paper. Let me actually close this entire thing. So, yeah, this one, understanding FFT's windowing. Like I can't access this entire thing because I'm located not in a civilized country, but I used a little bit of a VPN magic, right, and I downloaded this specific PDF, right, so I'm gonna actually open new PDF and I'm gonna invert the colors so it's not too harsh, but if you are located in a civilized world, you should be able to actually access this specific website and download this specific PDF. I'm gonna keep it in the description for all of you civilized people in civilized world. Right. So, and this one is actually really interesting. So they explain how FFT works, like how a signal is constructed out of several sine waves and stuff like that. Here is the, like a square signal, and this is how many sine signals it actually, like how many frequencies you need to add up to get the square stuff. And so one of the things they're talking about windowing, right? So there's a whole section, yeah, windowing. And it solves a very peculiar problem, right? So let's actually try to explore what kind of problem does it solve. Let's go back to like a drawing board and create a simple application that generates the sounds and takes a FFT of that sound, right? It's not really, we're not going to play any sound, we're going to just generate a signal and we're going to print that signal. So I'm going to do something like foo.c, right? So let's include stdio and there we go. So we're going to have something like n, which is going to be maybe it doesn't have to be power of 2, right? So because we don't have to use FFT, right? We can just use DFT, and DFT works with any amount of samples, so let's actually make it 30. Right, and so, and let's just have an array that will hold a signal, and let's generate some signal, right? So let's actually generate some signal. So I'm going to iterate through each individual sample in here, right? Like so. And then I'm going to take the normalized value of that index, right? So basically it's going to be I converted to float. It has to be float divided by n. And then I'm going to assign this specific thing in here, right? So it's going to be sine wave 2 multiplied by pi multiplied by t, right? So basically it's going to be a sine wave of a single period, right? So it's basically 1 Hertz frequency, right? And after that we want to print this entire thing, right? Let's actually display that signal, and it's going to be printf, like so, in I. Cool. So we probably need some math, and let's try to build this entire thing. So it's clang foo.c, and let's run this entire thing. So it doesn't have pi. I think a non-standard extension is to have m_pi. It's not particularly standard, but I just like don't want to spend time like defining pi or anything like that. There we go. So it doesn't have sine f, and this is because we never linked with the mathematical library. So there you go. So in here we have like a, you know, basically 1 period of a sine wave. It's kind of difficult to see this entire thing, like you can see the numbers, but it would be nice to maybe visualize that sine wave somehow. Right, so one of the things we can do is essentially, depending on the value of in, we can print the corresponding amount of characters, and that will sort of create an ASCII representation of a sine wave. Right, but we can't really do anything like for sort of size j equal to 0, j less than I, and multiplied by some sort of width, we can say like 10, and just print this entire stuff, you know, with stars or something. We can't really do that because in can be negative. The value of sine can be negative, right? And so how do you do a negative value in here? So I think it's going to be basically cut off. We can try to do that. That's actually very interesting. So you're not supposed to put a new line in here, of course. Right, you're supposed to put a new line in here. I'm kind of curious how it's going to look like. Yeah, so you can only see like a first half of the sine wave, right, of the first half. Maybe this particular width is going to be equal to n, right? So however many samples you have, also this is the width of this entire thing. Right, so yeah, there we go. So this is only the positive one, and negative one is kind of cut off. So one of the things we can do, essentially, we can add 1, effectively turning that range -1, 1 to from 0 to 2. And after that, we can divide it by 2, bringing it back to 0, 1. And that way, we'll be able to see sort of both of the sides of the wave, but it kind of looks weird. Right, so yeah, it kind of looks weird. So you kind of have to ignore the inner things in here. But maybe for the inner things, we could have just used spaces, and at the end, we could have just like put star. And there we go, here is the sine wave. Here is the sine wave. We can make it a little bit more frequent, right? So for essentially multiply by 2, and it's going to be 2 periods in here. So as you can see, there are 2 periods, and we can clearly see all of that, which is actually kind of cool. And here we essentially have a frequency, right? So we can even have that as a parameter in here. So frequency 2. And we can actually tune that. We can actually control that. We can have frequency 3. Right, so there will be 3 periods in here, but let's actually focus on a frequency 1, right? So it's a 1 period within a single sort of like a window and stuff like that. So maybe it makes sense to extract that to a separate variable, so it's a little bit more readable. You know, the subjective category, like readability. And the thing is about this specific wave, that specific wave, is that you can repeat that, and it's gonna basically have no seams, right? It can be seamlessly repeated. So, and we can literally just repeat that 2 times, right? So let's repeat this entire thing 2 times, and let's see how it's gonna look like. Right. So, and essentially, f of t and d of t and stuff like that, when they're computing the frequency, they kind of expect that the window on which they're computing the frequency is indefinitely repeating itself. Right, indefinitely repeating itself, and they're basically computing the frequency for this like infinite time, right? Where that specific window keeps repeating itself over and over again. Right, and as you can see, this entire thing repeats perfectly, right? But what if it doesn't? Right, what if there will be some sort of a situation? I think you can create that situation by having like frequency not integer or something like that. You will have a tear, and that sort of jump actually creates additional frequency that is not there. Right. So essentially these weird, things at the edges of the window, if they don't really seamlessly like continue, they create frequency that are not there. And D of t and F of t can actually pick those weird frequencies up. They can actually pick them up. So we can demonstrate that quite easily. So let's actually take DFT, right? So, and we're going to be using DFT because the size in here is not power of 2, but it doesn't really matter, right? So it's so small that it's not going to be like a very performance heavy in any case. All right, so let's actually have the complex output. Right, so you're supposed to do it like that. There we go. So here we computed the signal, and after that we want to do a DFT of that signal, right? So we want to transform the time domain into the frequency domain, right? So I'm going to put this entire thing in here. So this is the output and this is the N. And then we want to output all of that. So how we're going to be outputting all of that? I suppose we're going to be just like using the magnitude of the complex number. Right, so let's actually display it like this. We're going to iterate through all of these things. And we can use a similar trick, I suppose, right? So we can, well, let's just print a value first, right? Let's just print a value and see how it looks like. Okay, so it doesn't really compile because we don't really have complex numbers. Let's include complex numbers. So this is just a pi. Let's multiply by m pi, not me pi, m pi. Okay, so we have some stuff in here, and yeah, this is because I wanted to do CABSF. All right. Okay, there we go. So it's kind of difficult to see stuff in here, right? It's kind of difficult to see. So let's do the similar trick as we did in here. Essentially, we want to transform this value into like a factor, and then we basically do an ASCII art, right? So let's just like do an ASCII art. So, but we have to normalize this entire thing. We have to normalize this entire thing. I heard people just take a logarithm of this entire thing, right? So does it really help? It's still kind of big, so it can be actually over 1, so I don't think it's a particularly great idea. So we can do the following thing. We can try to compute the maximum of this entire thing. Right, so we can compute the maximum. So it's going to be float a. So if maximum is less than a, maximum becomes a. And after that, we can try to display that one more time, because now when we're getting that value, we can divide it by mx, and it's going to be from -1, from 0 to 1, right? So, and that's basically what we want to have in here. And we can do this thing essentially. So this has to be more of like a, well, like a j. We'll multiply by t. And we're gonna just print stars in here, and we're gonna do print cap. There we go. Ah, what the hell is? Oh no! Oh no! 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 Please don't tell me that I have to kill my Emacs. No. I had to kill my Emacs. That's what you get for copy-pasting code. That's what you get for copy-pasting code. Don't copy-paste code, kids. Don't. Yeah, this is because I have J in here. I forgot to. Yeah. And I just literally killed Emacs. Get freaking damn it. Get freaking damn it, mate. So clang O full C, and let's just try to run it. I hope it's not gonna die this time. And of course, it doesn't have DFT. What? Oh, this is, yeah, it says it doesn't have C expression in DFT, right? So because we have to link with math library, there we go. Okay, so we see the frequencies, right? We see the frequencies and stuff like that. But as you can see, they're mirroring, right? So there's high frequency in here, high frequency in here, and this is because we can ignore the second part of the frequencies, right? So essentially, I'm gonna just like divide this entire thing by 2. Doesn't really matter. So here are the frequencies. Maybe we want to separate them with some sort of a line, you know, some sort of a line, so we can distinguish them. Okay, so let's get rid of that tear between, you know, between the windows, right? Between the windows. So let's just use frequency 1. And as you can see, FFT shows perfectly 1 frequency. It shows perfectly 1 frequency. As soon as you tear it a little bit, it starts showing these phantom frequencies. Like they're sort of like basically get smeared across of the rest of the things. Like we don't have any of that stuff. And that stuff comes from these tears. Right? The DFT starts to think that these are additional frequency, and here they are. Here they literally are. So maybe we can even offset this entire thing, but I don't think if offsetting actually do anything. But yeah, so it just like looks a bit weird. What if we have a little bit higher frequencies? Right, yeah. So, and my hypothesis that those like flickering high frequencies, they're basically one of these things, right? If we have a lot of different nodes playing simultaneously, all of this additional smearage can like overlap and stuff like that, and it kind of looks weird. So maybe that's the problem. So the way people usually solve this problem of tearing of the window of FFT is by applying windowing function. So in the windowing function looks like this. Right, it's one of the famous, like favorite, one of the common windowing function is Hanning window, right? Hanning window, and it's basically like a cosine bell, right? Sometimes it's called Hann function. So I'm gonna put this thing in the description. I don't think I have that in the description, so let me actually put that in the description. Right, so Hann function. So this is a Hann function. So, and it looks like a cosine bell. You literally multiply your window by that thing, and effectively your signal turns into this thing. So you basically narrow it at the left and right side of the window. So if you have any tearage, it will actually smooth it out. And the cost you pay is this additional 1 Hz frequency that goes across your entire window, which is not going to affect like that much, right? So it's just additional frequency that you can basically ignore, but it smoothed out the rest of the things at the edges, right? Effectively getting rid of this sort of like phantom frequencies that are not really there and that are caused by, right, the window not being concatenated seamlessly, right? So which is actually kind of cool idea, right? So I would never actually come up with something like that, right? Because I don't really work in the area of signal processing or anything like that. So this particular document, this particular PDF document, like explains it really well. It's really good. I recommend to check it out. I really recommend to check it out. So we can give it a try, right? So let's take a look at the Hann function. So it is available in NumPy, by the way, right? So NumPy is very often used for signal processing, like for anything mathy and scientific. So obviously a Hann function is available there, right? So and so since I'm referring to this thing, it probably makes sense to Hann, to put it in the description, NumPy Hann. So, and the formula is rather straightforward, right? It is rather straightforward. So you basically have n that goes across your entire window, and you just plug it into this thing, and you basically have the Hann window. That's it. It's actually pretty straightforward. So we can even draw it out. We can draw it out. So let me give it a try. So I'm going to do return 0, so effectively deactivating all of the code below, right? So I want to ignore it for now. And I'm going to be iterating through the entire window, right? So let's actually iterate through the entire window. And in here, we have T. So interestingly, so N is the thing that goes across the entire window. And instead of the cosine, we effectively have n divided by the size of the window. So this entire thing is a normalized like value that goes from 0 to 1 as you goes across the entire window. So it's effectively t, right? It's effectively that. So, but they, for some reason they do -1. I'm not really sure if it's necessary actually, but they do that anyway. So maybe we can keep it as well. So, and the rest of the stuff is effectively just cosine 2m pi multiplied by t. It's like literally that, right? It's just like it's a sine wave, or rather cosine wave, with a frequency of 1, right? But it's also multiplied by half and subtracted from half. I have mosquitoes in here because I have a window opened because it's so hot. God damn it. So you have to choose between actually dying from a heat or dying from being eaten by mosquitoes, right? So that's the decisions I have to make in life, while also trying to fix my FFT visualization. God fucking damn it. Anyways, so let's go ahead and just like do that. And so we have to multiply by half and subtract it from half. And this is the value of the Hann function. And if I understand correctly, this value is basically from 0 to 1, so we can already use it for ASCII stuff, right? So we can already use it for ASCII stuff. And let's just print this entire thing with stars, and at the end we're gonna just put a new line in here, and let's just draw it. Let's just draw it, and it looks like scheiße, because I'm not using Hann, I'm using T. There we go. So this is basically cosine bell. We take our signal, we multiply it by that, so it turns into this like thing that starts from 0, then expands, and then goes back to 0, right? And then it actually concatenates with itself seamlessly, right? So that's basically the idea. So it's kind of interesting how this entire thing is constructed, right? So like, why do you have to do it like that, right? So essentially, if we just like take cosine, right? If we just take cosine, it's not really gonna work, right? So first of all, you're not gonna even have like a negative part, right? You're not gonna even have a negative part. So they effectively flip cosine around. They flip cosine around by subtracting it from 1, right? But now this you have a value from 0 to 2. And then what they do, they divide this entire thing by 2, normalizing it back to 0 to 1. And if you basically redistribute this division by 2, right, you end up with 1 divided by 2, which is exactly half multiplied by half. So they constructed this cosine bell by flipping cosine and normalizing it. So yeah, it's actually a pretty straightforward formula, right? It's kind of cool. I really like that. Anyway, so let's take this formula and apply it to our signal, right? So here's our signal as we generate it. So I think we can apply the Hann window like during the generation, right? But we have differences between t in here. Like, does -1 for n make any freaking difference? I feel like it doesn't. I don't feel like it's... Is there any difference between -1? I don't think so. I think we can just like use it as usual. Like, I don't really understand what's about this -1. I really don't. So in that case, we can just like use Hann and multiply it like this, right? So I think it's fine. I'm not an expert on like a signal processing or anything like that, but I feel like that -1 is not particularly necessary, right? Especially if you understand how this cosine bell is constructed, right? So our goal is just to have something that will be 0 at the beginning and 0 at the end, and it's just like becomes, you know, the maximum in the center, right? Sort of like a bell. But it also has to be like a 1 Hertz signal. So we're just trying to smooth things out, right? We're just trying to smooth things out. So let's actually take a look at how the entire signal is going to look like without a DFT. So let's make a frequency of 1 so we can actually see that. All right. So yeah, so it doesn't really have the it looks a little bit weird in here, but it's just like, yeah, it's smooth, more or less. It's smooth, more or less. If it's like 3, yeah. This is how it looks like. This is how it looks like. So we're trying to smooth it out at the edges of the window, if that makes any sense. So let's enable DFT and see how it works, right? So if we disable the Hann window, these are the frequencies without the Hann window, right? So there's some phantom stuff in here. If we enable Hann thing, it actually becomes a little bit more tidy. So you may see that there is like this sort of like additional phantom frequencies, but the frequencies we're generating are actually fractional. So maybe it kind of makes sense. So we have less spreading from to left and right. So it keeps it sort of like tight. So if I understand correctly, that's kind of the point of this Hann window, right? It keeps those frequencies tight, so they don't really spread anymore. So they're just packed tight. And as far as I know, there are different kinds of window functions for different purposes and stuff like that. But Hann function is the easiest one to implement because it's just like a flipped cosine and normalized, right? So, and this is probably something that we're going to use in here, right? And it's super easy to construct ourselves. So, yeah, that's basically windowing in signal processing, and that's why people do that, right? Because it's very non-intuitive thing. Right, so you wouldn't like guess that sort of like this thing, the tearing of the window at the edges causes like additional things unless you worked with the signal processing like long enough. Like I certainly didn't know that. I just started to Google how people use FFT for sound visualization, and I just stumbled upon something called windowing. I read about it and I'm like, holy shit, like I would have never thought about it unless I, you know, worked with this kind of stuff. But I suppose it's a common problem in signal processing, which is like really understandable, and it does make sense, right? It is an actual problem. So anyway, let's actually try to apply that window for our application and see if it improves the visual of this entire thing, right? Does it even improve anything? I don't freaking know. So the only thing we need in here is a Hann window. So let's go to plug, and where do we do all of that? Where do we do all of that? Okay, Gun. How are we gonna even approach this entire thing? I suppose we kind of have to maybe... I'm afraid that we can lose some information, right? If I just like go ahead and iterate through the input in here, right? So if I just iterate through the input in here and just multiply it by the Hann window, I don't think it's gonna work because we keep moving that window to the left, we keep shifting it, and I'm straight up modifying this entire thing. I think it's kind of dangerous. So one of the things I probably have to do, I have to have like a separate copy of input, I think. So let's give it a try anyway. So if I try to do something like float t, which is I, float multiplied by divided by n. Alright, so this is t, and we do have pi in here. It comes from Rayleigh. So, and then if I do I multiplied by Hann, I'm actually kind of like destroying information, right? Because, yeah, we're gonna keep shifting the windowed input, right? So we need to preserve the input without the windowing. So it's kind of important, I think. So let's try to compile this entire thing and see if it's actually doing anything. So build.sh. Let's just run build mutualizer. There we go. And where is my... Okay, I don't have a file manager, PCM FM. So give me some music. Yeah, it doesn't really help that much. It doesn't really help that much. So let me see what we can do. It's just like it's going crazy. It's freaking going crazy. So if we have input, right. So maybe we have to have input 1 and input 2, right. So essentially input 2 is going to be the windowed input. Oh, we can kind of see the nodes in here, right? So we can see them. All right, so let's try to compile this entire thing and go to the compilation errors. And what do we have in here? So yeah, we're going to be pushing everything into input 1, right? So that's one thing. Everything here is input 1. And we're going to be applying the Hann window on input 2. So maybe one thing we have to do is essentially input 2 is equal to input 1 multiplied by the Hann, right? And we're doing FFT on input 2. So input 2 is windowed, right? So, and let's see. And the phantom frequencies here disappeared. So that was literally the problem, right? So that was literally the problem. Isn't that poggers? Isn't that poggers? I think that's pretty freaking poggers. So yeah, that's the magic of windowing. That's why it's so important. So you don't have some phantom shit. Alright, that's pretty poggers, my friend. So, another thing that we probably need to do. So there's another article that I found online that basically talks about FFT and visualization. It's called A Better FFT Based Audio Visualization. I'm also going to keep it in the description. So there is another interesting idea that is basically mentioned in this particular article. It's a power scale. Right. Essentially, it's a scaling these amplitudes in here. So they suggest that you do basically logarithm on them, because the bigger the frequency, they kind of grow exponentially. So the more powerful frequency like really overwhelm the less powerful frequency, so you can't see them anymore. Right, and because of that, you can see this like very high peaks and stuff like that. So one of the ways to combat that, what they suggest is basically do a logarithm on the on this bar, right? So we can go ahead and just try to do that. So let me see. So we can take amplitude. So here we take C IBSF and basically do like a natural logarithm on that, right? And see if it's going to fix anything. So that's very interesting. Right. So I still feel like we have something weird in here, and this is because we don't really cut off all of the reflections, right? So what I want you to do, I want you to ignore some of this stuff. I'm not 100% sure what is going on in here, right? So, but there's something weird in here, right? So, but if I remember correctly, they were suggesting not only taking like a logarithm that, they suggested to take a logarithm on a square of the amplitude, right? So let me see if squaring that thing is going to help. Right, let me see. So we can basically take A, please uncomment that. Right, so we take A, and we can take a square, which effectively means like, that means we can get rid of the square root in here. Right, we could have just like taken A and C real F, just take the real part, right, just take the real part, and then imaginary part, imag, and just do A plus B, B, and that's already square of the C abs, right? It's already square of the magnitude, so you can kind of like save on calling to a square root, but I don't know how exactly CABSF is implemented. Maybe it doesn't really call to square root, maybe it's not that expensive. I wonder if that's going to help. No, it didn't really help. Yeah. But it already kind of close to what we saw on this website. Right, I want to wait for the moment when individual nodes start to play, right? Because this is where it's going to be visible whether it actually works or not. It's kind of close. It's kind of close. So I think it's better, right? So let me see. So it also has like a similar shape as in here. Right, but this one is a little bit more interesting, I think. Yeah. So all of these tricks are kind of work, like they do kind of work. So, which means that we may be on the right path. So another thing that I didn't do is I didn't like cut this in half. I think maybe that's what I forgot to do. Alright, so just a second. I'm gonna restart the mutualizer. I'm still not sure about this. Like, where is that stuff coming from? So it's not supposed to be there. So we can try to maybe bring this entire thing down, right, at the bottom, just keep it... Alright, and this one is rather big. Right, we can keep it in here. We can listen to different things, for example, from the work in progress. What's the size of the window in here? It's 13. Okay, so that's fine. I think 13, 2 to the power of 13 is actually the best one. I think I know what's the problem. Yeah. So I yet again, made a wrong assumption about API of Raylib, specifically sound API. For some reason, for me personally, the sound API of Raylib, it's not particularly intuitive. I keep making wrong assumptions about it. So yeah, We already discussed that in the comment section. Somebody mentioned that in the comment section on YouTube. So I basically try to interpret the data that I receive from the array-lib differently depending on the amount of channels I have, like basically we read from the file. But it probably normalizes everything, and it probably always keeps the amount of channel to 2, even if you supply like a mono music to it, right? And I wonder if the burden of truth, the music that we're listening to like for testing, is actually mono. I don't quite remember, so let me take a look at ffprop. I think it's mono, right? Maybe it is mono, right? But it is always, I think it is always stereo. I think array-lib actually always normalizes to be stereo. Right, so let's actually try to recompile this entire thing, right, like so, and let's start the visualizer. And I think this is the reason why we have like weird stuff at the end, because it doesn't really visualize the, you know, the correct stuff, right? It doesn't try to do FFT on the correct samples. Now we're talking, right? So that was the problem. Thank you so much, whoever mentioned that in the comments. Right, so. And I think it's already close to whatever we have on the Battle of Beats. The visualization on Battle of Beats is still better, but I think this is like a huge step forward. So let's wait. Look at this note. So by the way, do you know why it looks like this? Even though it feels like it's playing a single note. It feels like it's playing a single note, though you see several of them. So there's other songs in here that actually kind of make it even more obvious. You can literally see that, and they sort of form this like, you know, how to say that, like a slope or something. And that effect is actually explained in this paper, in this PDF paper, which explains windowing and stuff like that. Right, so the reason is because these are square waves. Since it's a chiptune, it makes use of sine waves, square waves, sawtooth waves, and stuff like that. And this is basically a signature of a square wave, right? So how can you construct a square wave out of sine waves? Right, you have to have a lot of these frequencies that will add up eventually to this, right? So this is basically all of the frequencies that you need to have to construct this, to construct just this. And because of that, if you display all of these frequencies in a frequency domain, you will have this rump that looks like this. So basically they even mentioned that. If you see a nice rump in the frequency domain, you know the original signal was a square wave. Again, chiptune, primarily square waves, sawtooth waves, just, you know, pure sine waves and stuff like that, right? So it's a very simple waves usually, and that's the reason why we see that, right, when we try to play things like that. We see nice ramps. We can literally see them. It's actually so cool. All right. So I think, yeah, so this is basically everything that I want you to do on today's stream, right? So I basically want you to apply all of the tricks regarding FFT that I found online, right? Because just knowing FFT is really not enough, because it's just like theory. When you try to apply FFT in practice, it's completely different story, right? You have to know all of these like little tricks, like scaling properly, scaling in frequency, scaling in power, right? So windowing and stuff like that. Just by knowing FFT, right? It's not enough. You need additional things. So, and that's the difference between theory and practice. So yeah, that's basically everything that I wanted to do for today's session. Thanks everyone who's watching right now. Thank you, Null, for making an awesome music. And I see you all on the next recreation programming session. Love you all. Mwah.